Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. In the near future, spacecraft could take just a few months to reach the outer edges of our solar system, rather than the years that it currently takes. They could do this by riding a beam of laser light. It might sound like science fiction, but often ambitious scientific programs are there to push the boundaries of what is possible and invent new technology. The spacecraft would be comprised entirely of a membrane with sensors embedded in it. A new device is being created to measure the radiation pressure in this membrane, known as a lightsail, and the device is made from the leading material for this application, silicon nitride. Professor Harry Atwater from the California Institute of Technology explains why this material is important.
Silicon nitride is a material that's used in thin films in microelectronic circuits. The methods of fabrication of thin films are well developed. They're used also in another research field, which is quantum optomechanics. This is an area where physicists are interested in cooling down mechanical structures to their quantum mechanical ground states. And this requires very low dissipation, very, so to speak, low noise material. So you can see individual mechanical quanta. And it's that field that really pushed the limits of developing silicon nitride as a material. And that was one of the reasons that we chose silicon nitride as a lightsail material. But the characteristics of a lightsail as propelled by radiation pressure had not previously studied.
For space applications, the deployed lightsail would measure 10 meters squared and be just 100 nanometers or less in thickness. For now, the experimental device that is being developed to measure forces with incredible sensitivity has a square profile measuring just 40 micrometers wide. The device incorporates springs at each corner of the lightsail, etched out of a single sheet of silicon nitride and tethered to the support frame. To measure the displacement of the lightsail when exposed to a high-intensity laser, a bespoke interferometer was created that could account for the inherent vibrations of the atoms in the silicon nitride and measure displacement with picometer resolution.
So what we actually do is a two-beam interferometry experiment where we use one beam that is on the rigid part of the silicon frame. That's oscillating too in the lab, unavoidably, just because everything oscillates. Everything vibrates. But we can measure the relative displacement of the membrane relative to its rigid frame. One beam goes onto the membrane. We can focus with a diffraction-limited beam spot, so we can actually profile the displacement across the membrane. We can watch the modes the membrane will exhibit, so the fundamental mode or the higher order modes that have torsional oscillations.
Observing these modes provides insight into how the lightsail would behave during flight. Riding a laser beam that originates on Earth means that the lightsail may not always be perfectly aligned with the beam. The incident angle and spot size were varied, which revealed a non-intuitive trend that was understood using mathematical modeling.
At the edges of the sail, what we found was, as we illuminated it obliquely, the beam spot size is elongated by a cosine expansion of the beam spot size. So what happened was part of the beam was actually scattering from the edge of the membrane. So at the edge, you get something other than just a specular simple reflection. You get more complex scattering forces.
Creating a patterned membrane, one that resembles a diffraction grating, also allowed for in-plane motion to be measured and showed that the lightsail wobbles as it moves along the optical axis. This comprehensive analysis of the dynamics provides a thorough understanding of key parameters that are essential for lightsail propulsion and paves the way for the next step of research, untethered flight. The research also provides a platform for probing optomechanical properties of membranes on a macro scale, which complements work on the micro scale to develop optical tweezers. These advances are made possible by collaboration, and Professor Atwater points to the efforts of other investigators in the team.
The work depends on the indomitable spirit of young people. Two people I'll mention who played a major role in that work are Leora McKelly. He's currently a postdoc. He will soon be a starting professor at Tel Aviv University in Israel, and Raymond Gao.
This work was published in a recent issue of Nature Photonics. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.